So that's what I wanted to talk about there. All right, now I need to spend some time on 1.2. I know it's not due yet. Feel free to write down anything, and we're going over this together. But we definitely need to talk about number 5, and we'll touch a bit on number 6.
Wait, it's on number.
This is 1.2. This is 1.2 homework question number 5. So this one isn't due yet. If you've done it already, kind of check your work. If you haven't done it, you do it right now. Okay? Alright, so here's the deal. We're to describe the discontinuity as removable or infinite, and where is it? Now, this is on me. We talked about removable discontinuities, right? Where do they look up in the picture? The whole. But I didn't ever tell you how we got it. So we need to discuss them. So we're going to use problems A and B as our examples to talk about whether discontinuities are removable or not. So I want you to look at the problem. Do you notice that it factors? It got so hot in here, I opened the window. Of course, not even excited about grass. Okay. Now, does anything cancel? No. The word removable means that the problem, the discontinuity, can be removed from the problem. Nothing can be removed here. So you are going to have 2 vertical asymptotes, one at -2, x equals -2, and one at x equals +2. These are infinite or non-removable discontinuities. They are graphed as vertical asymptotes because you are stuck with them. There is not a darn thing you can do to get rid of them. They are there. X will never be -2, X will never be 2. Lucy?
Wait, so will removable discontinuity will not have a class to at all?
Okay, just wait a second. Do you understand this one so
Yeah.
far? Okay, let's look at B now. Because B is a different situation. Can we factor everything just like we did over here? Yeah. So we'll do that. We will factor our problem. Difference of squares on top, and then on the bottom. Now, at first glance, to the untrained eye, it looks like we're going to have 2 vertical asymptotes again. But upon a little bit closer examination, what happens here? Those cancel. So the problem actually reduces to x plus 3 over x minus 1. So this is really our problem because we removed that issue. Now, when you remove a discontinuity, it looked like in the beginning this was going to be a cannot be, x can't be 3. Well, x still can't be 3 in the original problem. But can x be 3 in this problem? So that will be graphed. If x is 3, what would my y be if x is 3? Oh, you get 6 over 2? You get 3 for that also? Coincidence. Put 3 in here. That becomes a hole in the graph. It isn't as powerful as an asymptote because basically we removed it from the problem. But in the beginning, the original problem that you are graphing, you could not put 3 in because you would get a 0 in the bottom. But because you could remove it, you're going to go ahead and plot it as an open circle.
How'd you get 6 over 2? What's
X is 3. X is 3.
X is 3.
3 plus 3, 3 minus 1. 3 plus 3 is 6, 3 minus 1 is 2, right?
Couldn't X also not be 1?
Well, I haven't gotten there yet. I'm talking about the removable discontinuity. So this is how you get a removable discontinuity, a hole. You cancel it out of the problem. It's still a gap, but it's not a complete break like an asymptote is. Now, could I get rid of the X minus 1? No. So that stays, that's a non-removable or an infinite discontinuity at 1. So this problem has 2 discontinuities, just like this one did. But in this case, one of them is removable. You have a hole at 3, 3. And the other one is not removable, it's infinite. You have a vertical asymptote at X equals 1.
So is it both removable and infinite discontinuity?
Non-removable and infinite describe the same thing. So you don't need both words, you can easily do word. Non-removable and infinite mean the same thing. Just like removable and whole mean the same thing.
So you read both of them.
See?
So you got X equals 3 because that is what you cancel
Yep.
out? Okay.
Yep.
So whatever you cancel
If you
out,
cancel it out, it becomes a whole.
So there's 2 discontinuities are 1 and 3.
You need to talk louder.
There's only 2 discontinuities, and that's 1 and 3, or did we say 3?
Yes, those are you were told to describe it as removable or infinite. And this is it right here. You've got a removable one at 3, 3, and you have a vertical asymptote, a non-removable one at 1. Marin?
Would on the top, like X plus 3, is that just like irrelevant, I guess?
Yep. I mean, I needed that to find my y coordinate of my hole, but it has nothing to do with discontinuities. Where do discontinuities come from? Denominator can't be, see what, it has nothing to do with the numerator. Finley?
How do we answer this question? Do you just do removable 3, 3,
Well,
infinite, X
you have an
equals
infinite discontinuity at X equals 1,
It's a both, and then a removable 3, 3.
and then a removable at 3, 3. Yeah, that's why there's 2 blanks there. So you have a-
Okay, sorry, last question. So if you cancel multiple things out on the bottom, then there are multiple removable
Yep.
discontinuities? Okay.
You can have, depending on the problem, you can have as many holes and as many asymptotes as there are in the problem.
And so we write it as an ordered pair or
Yep.
an X equals 3.
Well, the discontinuity is at X equals 3, but when you're giving its type and location, it would be 3, 3. So a hole at 3, 3.
Would you say non-removable at X equals 1, or would you say vertical asymptote?
Whatever you want to
Either
say,
one.
or infinite discontinuity. It all means the same thing. The idea is, we're heading toward graphing these things, so you know that's what you have to put in your picture there. Okay? Now, caution, your calculators do an awesome job, the new calculators do an awesome job with the asymptotes. I am not sure, I don't think they caught the whole. So I think that's something you're gonna have to be aware of, even if you're typing it in on your calculator. Okay? So, moral of the story, discontinuities cannot be's. Your graph breaks when you have an X can't be something. There are varying degrees of can't be's. There's the absolute can't be, which is your non-removable, infinite, vertical asymptote discontinuity. And then there is the sorta cannot be's that we cancel out of the problem. They cannot be in the original, but they can be in the reduced problem. So that is graphed as a hole. If you cannot cancel, you do not have a hole. So most problems don't have holes. You have to be able to cancel for that to happen. Okay? All right, one more, Lucy.
And if it's the jump discontinuity, is that like, it's like jumping from a hole to a
Yes.
new line?
Right.
Okay.
Okay, all right, now I want to look at number 6 only because we never actually graphed maxes and mins. We did graph zeros and points of intersection, and it's all the same way. It's all in the same menu. So let's look at problem B. This is 6B. Go to y equals and type it in. Negative x cubed plus 2x minus 3. I'm going to zoom 6 to have a nice square window. And I got a picture that looks like we're on 1.2, number 6. B, 6B. Did you get a picture that looked like that? Now, when we were doing this before, we were looking for that point right there. Right? So how did we find it? We did second, calc, 0, and then left bound, right bound. Okay. If we're looking for the minimum, the relative minimum, which would be this valley right here, we're gonna second, calc, min, left bound, right bound, yes, and it's going to give you the point. I got for the min negative 0.816, negative 4.089. Does that sound about right? That's what I have written down on my paper.
Wait, so is minimum the first curve?
There's no first, there's only one curve, Lucy.
Yeah.
This would be the minimum, right? That's the low point.
Wait, did we do?
And then to get your maximum, which would be this point right here, we're going to second calc max and do the same thing. Left bound, right bound. It's exactly like finding a 0 test.
It's not even air bound. What is that?
Okay, that means if this is the minimum point you're looking for, you have to have left set over here and right set over here. You apparently don't. Sydney?
So for these guys, do we write it as y equals or in order?
Ordered pair.
Okay.
You're finding the minimum point.
This is 4. Okay.
Okay, if you, bring it in, bring it in. Come by after school, we'll look at it, okay? We gotta get moving, I can't do all this calculator stuff.
Minimum and maximum?
It says find all extrema. When I look at this picture, I see a relative minimum and a relative maximum, right? So depending on the picture, you might have more than that.
But if it's like one of those words
All right, if you're having calculator issues, come by after school, or maybe at lunch, we can get it real quick. We gotta get some problems done here. One more comment about this. This is one of your BFFs. Which BFF is this? The cubing function. Does it make sense that it's in this direction? Because your regular BFF looks like this. Does it make sense that this one is going that way?
It has a negative.
It has a negative in front. And what does a negative in front do?
Flip.
Turns it upside down. So instead of being an increasing function, it is a decreasing function. Also, the other stuff they put in the problem, the plus 2x minus 3, that's why it has this waviness in it. If it didn't have all that junk in the middle, it would just be more straight. It wouldn't have that defined maximum and minimum, but it does. All right, so now you're on your own, or you can come in for office hours or something to look at that. Now we need to get back to work. So get your notes out. We're going back to work here. We're going to look at a couple of piecewise functions. And they're called piecewise functions because they are done in pieces. These sometimes Very often they are not continuous, but they certainly can be. All right, so you see two pieces? All right, so here we go. If you were just walking down the hallway and you found this all by itself, just this right here, none of us stuff, just that, what would that look like? That would look like an upright V from the origin, right? So it would look like this. Now, y'all using pencil, I'm using an erasable marker, everything's good. This is what the picture would look like if this is all I have. But I have this over here, which tells me that for this V, I can only consider the part of it where X is greater than or equal to 0. So in other words, I can only look at this part of the V. Would you agree with me?
Yep.
So the first piece of my graph, X is positive, it's an absolute value curve, which is just that little vector shooting up there. Now, what if we found just this in the hallway? What shape is that?
Upside down parabola.
Upside down parabola, vertex at the origin. So if I had the whole thing, it would look like that, right? But I'm only allowed to include the part of that parabola where X is negative. So that means I can't look at this part over here, and it doesn't matter in this case, but see there's no equal to on that? So as far as the parabola is concerned, that dot's open. So this would be this part, right? However, since that dot has already been colored in, I don't need to worry about that. That is a solid dot, that's colored in. And because it's colored in from the first part of the graph, is this a continuous function?
Yes.
Yeah, so even though I graphed it in two different pieces and it has two completely different, components, they connect. That doesn't usually happen, but they connect this time, so there you go. What's the domain of this function?
Negative infinity to infinity.
Negative infinity to infinity, all real numbers, right here, kids. Isn't this your domain? That's everything, isn't it? What about range? Look at your picture. What do you think about range?
All real numbers.
Negative infinity to positive infinity. Very, very good. Very good. Okay, that's not bad. Let's get this one done before your lunch. All right, so here we go. Last one before lunch. This one happens to be in 3 pieces, which you can make them as many pieces as you want. Now, you are free to approach these problems any way you want. Okay? You're free to approach them anyhow you want. What I like to do is to start off by noticing that it looks like the disconnect point for this thing is at -1. That's where things stop and start. So I'm going to go ahead, and it's not an asymptote, but I'm going to put a little squiggly line here at -1. It's not an asymptote. This is my style of doing the problem. You do not need to do this. What does that look like?
A V. That's a
That's
little
a
wider.
V shifted 3 units left. So if I were to graph, that's -1. So if I were to graph it, would it look like this? But I am only allowed to consider the part of this V that's that side of my squiggly line. So I'm going to put an open dot there. Do you understand why that dot's open?
It doesn't include.
And I'm gonna make this a little darker, and then I'm gonna erase all this, because none of that is part of the picture. Now, what does this part say? This is my black part. What does this part say? Y equals 5? Now, y equals 5 is a horizontal line across here. But I don't want the line at all. I only want the point, -1, 5.
Yeah.
So, solid dot, -1, 5. All right, what's this look like?
Y, so
It's a line with a slope of 2 going through the origin. So goes through the origin, has a slope of 2, so down 2 over 1, up 2. Okay, so I'm gonna do it nice and lightly here. It would look like this. Would everybody agree with that? But I don't want the whole line. I only want the part of it. Oops, I think, was that a less than, I hope, in the problem? It's supposed to be a less than. I need to fix that. That needs to be a less than. We'll talk about why it needs to be in a second, but let's finish the problem. That needs to be a less than. The problem won't work otherwise. You'll see why. Maybe you already know why. What part of this line do I want? Starting right here and going this way?
Yeah.
I do not want any of this. Now, technically, that squiggly line isn't there. So I'm gonna go ahead and pull it out. And there's my piecewise function. So each piece graphed to the right of -1, to the left of -1, and on -1. Definitely not continuous this time, right? So tell me why my mistake was absolutely idiotic and I should be embarrassed. Why? Oliver?
It has to be a function.
It has to be a function. It has to be a function. And if it has to be a function, then these values be x's bigger than -1 and these be x's bigger than -1? No. All right, quick. What's the domain?
All real.
All real numbers. Negative infinity to infinity. That's my domain. What's my range? Be careful. What's my range?
All real numbers.
What's this y value right here? That came from up here, wouldn't that be 2? So it's that's +2. So isn't everything from 2 to infinity? That takes care of this part, right? Or, what's this one? Isn't that -2? So negative infinity to -2. Because we have a gap in the picture. All right, back to 50. Back to 50. If you got a calculator issue, show it to me. Let's get that straightened out. And then I'll see you back here at 50 or whenever they kick you out.